In the previous section, you learned about how light behave as wave. In this video, we are going to learn about how light behave as photon or particle. Okay, so we are going to take a look at how light come in a discrete amount of energy, or what we call photon. Please read the OER textbook chapter section 3.2 for more detail of this topic. And you should be able to start working on paper homework chapter 3 as soon as you finish this. This video will cover homework chapter 3 numbers 7 to 10. The continuous wave model of light that you see in the previous video can explain the diffraction pattern and also the interference pattern very well. However, it's failed to explain some of other behavior of light, such as blackbody radiation, photoelectric effect, and the atomic emission spectra. First, we are going to take a look at how the wave model that we see previously failed to explain the emission of light from hot object, which is what we call blackbody radiation. Blackbody radiation is the emission of light from hot object, and the color of the object before it gets heated, most of them are in black color, so that's why it's called blackbody radiation. So as you see this the range right here, right? So as it gets heated, right, it's going to start to glow or emit light. And this light can be emitted in the visible light region and also in the infrared region as well, which is just the heat that we feel. Similar to the tungsten light bulb as well, as the tungsten element gets heated, right, it's going to glow and it's going to emit light in the region of visible light that we see here. And also it's going to produce the heat as well that is going to fall into the infrared region. Other objects can also emit light as well, such as our body. Our body emits light in form of infrared, right? So our eyes cannot detect it because infrared is not part of the visible light. However, we can feel it because infrared is part of heat, right, that we feel. The graph shown here is the blackbody radiation spectra. It's plotted between the wavelength in micrometer against spectral radiance. Okay, so this graph tells you about the relationship of the hot object at different temperature, and it tells you about what type of radiation is going to emit, right? So in this case, these color are going to associate with the visible light with different color. Okay, so for example, now if you're looking at the object that heated to 3000 Kelvin, right, you will notice that the light that is emitted from this hot object is going to give off various wavelength, but the one that is going to be the most radiance for this object is going to be those that fall into around the infrared region, right? You might be able to see the red color of this. Okay. So if you're looking at the object that heat in a higher temperature, let's say like 4000 Kelvin, in this case, you are going to see that the graph is shift a little bit, right? So toward more of the visible light region, right? So in this case, you probably notice that the light that is emitted is going to cover various wavelength, but the one that is going to be the most radiant is going to be giving off around this red-ish color right here. Okay, so if you're looking at those objects that is even hotter, like around 5000 Kelvin, you also see as well that the maximum radiant right here is going to fall around the wavelength that fall into like green region of the visible light. Right? So that means in this case, if you compare this to the star, right, you will notice that the blue star is going to be hotter than the yellow star because the temperature of the blue star will give off the blue light region, which is in a higher energy than the yellow star. So this graph that you see here has come from experimental observation. Okay, so if you tie this back to the classical theory, which is looking at light in terms of continuous wave model. Okay, so this theory right here is actually failed to explain this phenomena because if you're looking at the prediction from the continuous wave model theory is deviate from the experimental observation that we see here. And because the classical theory failed to explain this blackbody radiation around the ultraviolet, so we call this ultraviolet catastrophe. And in order to reconcile the idea of light behave as wave and also to help explain the observation from the blackbody radiation spectra, Max Planck proposed the idea of light as the energy in form of a packet, right? It's come as the discrete amount, and that is called quanta. Okay, so this wave model now is going to be look at quantized energy or the standing wave. So it's not going to be explained as the continuous wave. This quantized wave model is going to be a fixed amount of wave, right? It's going to be the standing wave, similar to how you walk up the stair, right? So every step that you walk up is going to increase in a fixed increment. So Planck used the idea of how light behave as quanta or the packet of energy, right, to explain the spectra of black body radiation, that energy could be gained or lost only in whole multiple of quantum. Okay, so it cannot be lost or gained with the continuous amount, like what the classical theory or the continuous wave theory explain, right? So which is incorrect here. Okay, so with his explanation, he stated that at the different temperature, an object will emit different maximum intensity of radiation. According to Planck's idea of light come in a packet of energy, or what we call quanta. In this case, we are able to relate the energy of light to the frequency of light, which is we are going to take a look at light in terms of standing wave, not the continuous wave. Okay, so what we are looking here is going to be the relationship that tell you about the energy of light and frequency of light. This H right here is a constant, is the Planck constant. It will be given to you on the exam. Okay, so it's come out to be this value right here. It's going to be in joule times second as the unit. And because the energy of light is quantized or come in a discrete amount, therefore matter can only absorb or emit energy in whole multiples. For example, it can absorb 1 h nu or 2 h nu or 3 h nu, 4 h nu, and so on. Okay, so it can only absorb or emit only in whole multiples. So here is the quantized wave model. Okay, so that is represented by fundamental wave, first overtone, second overtone, and third overtone. Okay, so according to Planck theory, right? So when you're looking at wave, right? So we're looking at the wave of light, right? So it's going to come in a quantized or a discrete amount of energy, and that is going to be E. Okay, so this is going to represent by E multiplied by h nu. Okay, so this is going to be the frequency that represent this fundamental wave. Now, if you're looking at the second one, right, so the first overtone here, you probably notice that the frequency is higher than the first one, right, by double, right? So in this case, you can say that the energy of the second one, so this is the energy of the first one, the energy of the second one, okay, is going to be the constant multiplied by frequency that is double from the fundamental wave. Now, if you continue doing this with the second overtone, the energy of the second overtone would be the constant multiplied by the frequency that is 3 times higher than the fundamental wave, right? If you do this same with the third overtone, you will see that it's going to equal to Planck constant multiplied by 4 times higher of the frequency in comparison to the fundamental wave, right? So you probably notice that the frequency is going to increase in a whole number amount, right? So in this case, so that means in this case, you probably notice that the energy of the fundamental wave would be lower than the energy of the third overtone, for example. So that implies that the higher the frequency, you are going to also end up observing a higher energy for that wave of light as well. So now if you tie back into the electromagnetic spectrum that we see earlier, this is why the energy is going to be directly proportional to the frequency. But remember, frequency is inversely proportional to wavelength. So therefore, energy is going to be inversely proportional to the wavelength. So now if you tie this back to the electromagnetic spectrum, right, you will see that the one that have a longer wavelength would be the one that would have the lower energy in comparison to those that have a shorter wavelength. They are going to have a higher energy. Okay, so makes sense, right? Because if you are using microwave at home, you don't need to use any protection. But if you go to do X-ray, right, you need to use lead to protect other part of your body that is not going to undergo diagnosis, right? So because X-ray has higher energy than microwave, right? Makes sense. Next, we are going to take a look at how the continuous wave model failed to explain the photoelectric effect, which is the emission of electron from metal surface when the light is shined on the surface of the metal. The photoelectric effect is the ejection of electrons from metal surface when light having a frequency greater than some threshold frequency was shown on it. According to the classical wave theory, a wave's energy depends on its intensity, which depends on its amplitude, not its frequency. What do we mean by that? Okay, so let's take a look at these figures right here. Okay, so pretty much the classical wave theory see that the wave, even though they have the same frequency, right, if they are brighter or if they have higher amplitude, they are going to contain or carry a higher energy that is going to be able to eject electrons from the surface of the metal, right? So regardless of what type of frequency that would be, as long as it have a really high amplitude or if they are very bright, right? However, the experiment confirmed that the ejection of electron did not depend on the brightness or the intensity of light, but increased with the increasing frequency of the light. So the classical wave theory that see light as the continuous wave failed to explain the photoelectric effect. Later on, Albert Einstein was able to resolve the paradox by incorporating Planck's quantization idea of that light come in the quantized energy or the decreased amount of energy. Okay, so pretty much he incorporated this idea that Planck has postulated in his treatment of the black body radiation, and he applied this to the photoelectric effect. And he proposed that the light that strike on the metal surface should not be viewed as a wave, but instead should be viewed as a stream of particle, which is what we call photon. And the energy of the photon will depend on its frequency according to this Planck formula right here. Now let's us take a look at PhET simulation of photoelectric effect. Okay, so this is the lamp that is going to generate light. Okay, so these two are electrodes. This electrode right here is going to be coated with metal. Okay, so this would be metal. And the type of metal that we are going to use, the first one would be sodium, and eventually I'm going to change it to platinum. Okay, but the first one, I'm just going to use sodium first. Okay, so, and both of these electrodes are connected to this battery right here that eventually we will be able to read out the current when there is the movement of the electron. Okay, so what I'm going to do is that I'm going to start with the longer wavelength, which is the lower frequency of light. I'm going to start at infrared region. Okay, so according to the classical wave theory that I mentioned earlier, right? So the intensity, the one that is higher, right, should be able to knock off the electron regardless of what type frequency that would be, right? So in this case, I'm going to crank the intensity up. Okay, so let's do like 50%. Okay, I'm going to play it. Okay, so nothing come out. I'm going to increase more to 100%. You probably notice that nothing come out. Okay, so I'm going to stop now. I'm going to continue to the next region of the light, which is the red light. Okay, so if I do this, I'm going to, let's say like decrease the intensity to about 50%. Nothing come out. Let's take a look at 100%. Still nothing come out, right? So that means in this case, the classical wave theory is failed to explain this phenomena because it doesn't matter what would be the brightness of light. Still, right, according to this, there is no electron is ejected from this surface metal because there is not enough energy for this region of light. So now what about if I decrease the wavelength, which is increasing the frequency? Okay, so I'm going to decrease the wavelength or increase frequency, right? So I'm going to decrease wavelength to, let's say 535, okay. At this point, you probably notice that the electron is start to come out. So that means at this point, at this frequency, right, this specific wavelength right here is having enough energy of a photon to knock off the electron from the metal surface, right? So you might wonder, oh, what about the intensity then? Well, you can decrease intensity to 50%, right? About 50%, you also going to see that the electron is still going to come out. Right? So that means in this case, intensity doesn't affect the ejection of electron, only the frequency that will affect the ejection of electron. So specific metal will require specific threshold frequency for electron to be ejected. Okay, so, and if I keep decreasing the wavelength or increasing the frequency toward the high energy of light, you are going to observe that there will be more electron would be ejected because the light that's shown onto the metal surface has higher energy, so they are able to knock out electron easier. So therefore, there will be more electron produced from that. And now you see the current as well, right? Because there are enough electron to actually producing that electrical current now. Next, I'm going to change to platinum. Okay, so I'm going to change this metal surface right here to platinum. And what we are going to do is that we are going to start with infrared again, right? With the high intensity, you probably notice that the amplitude or the brightness of light doesn't do anything. I'm going to keep increasing frequency or decreasing wavelength. You probably notice that for sodium, it start at 535 or lower for the electron to be ejected. But for platinum, right, 535 doesn't do anything for the platinum metal. So I'm going to decrease more of the wavelength, which is I'm increasing the frequency, okay, or increasing the energy of light. Still nothing come out. Still nothing come out. Okay, so that is violet region now. So nothing come out. So I'm going to go toward the ultraviolet region now. Here we go. So in this case, right, the minimum threshold frequency or the minimum threshold wavelength for platinum would be starting at 193 nanometer, right? So you will see that that's when electrons start to coming out now. Okay, so again, the intensity doesn't affect the ejection of electron, but the frequency does. Okay, so therefore in this case, we are going to take a look at the energy of electron that is going to be related to frequency, not the amplitude or not the brightness of light. Okay, so again, if I increase more frequency or decreasing more of the wavelength, you are giving more energy on the surface metal. Therefore, there will be more electron ejected. From the simulation, you can see that the continuous wave model of light, right, failed to explain the photoelectric effect because not all wave can cause the emission of electron, and also not all intensity of light can cause ejection of electron as well. It have to be at a minimum wavelength or frequency of light for a specific metal, right, that is going to be required for the emission of electron. And that minimum frequency is what we call threshold frequency. Again, it's specific for each metal. For example, sodium metal, right, so it's going to require the wavelength 535 nanometer or smaller, right, for electron on the surface of sodium metal to be ejected, right? So any wavelength above this 535, right, you will not observe any ejection of electron. Okay, so and for platinum metal, right, it's going to require the wavelength of 139, or which is related to UV region, right, or smaller, to cause the emission of electron from the platinum metal. Einstein's explanation of photoelectric effect is complementary to Planck theory that we see earlier. So he explained that light energy must come in a packet called photon, and these photons have to have a discrete amount of energy with it, right? So in other words, light was not like ocean wave, but it's more like particle. Okay, so it's come in form of particles. And the energy of light right here is going to refer to energy of one photon. Okay, so this equation only describes the energy of one photon. Okay, or one particle of light. The application of photoelectric effect can be found in solar cell. Okay, so for example, right, so when the light shine through the surface metal is going to emit electron, and that electron is going to go from one electrode to another, causing the circuit to complete, right? And that is going to generate the current, right? Which is the electricity. Now, before we get into the calculation, I want to go over what we have learned so far. Okay, so in chapter 3.1, we look at the relationship between frequency and lambda, which is the wavelength. And this chapter will look at the relationship between energy and frequency. So I'm going to tie all of these together. Okay, so according to chapter 3.1, we see that the frequency, right, is inversely proportional to lambda. So that means if you have high frequency, the wavelength is going to be small, right? So it's going to have a small wavelength. Now, if you're looking at the energy versus frequency, if you have a high frequency, you are going to end up with a high energy as well, because the relationship would be directly proportional to each other, right? So that means if you tie the energy back to the wavelength, the energy and the wavelength would have the inversely proportional relationship, right? So if you have high energy, that wave of the wavelength of light is going to be small. You probably notice that this frequency right here and this frequency, they are the same. So therefore, in this case, I'm going to replace this term to this term. Okay, so therefore, another equation that I can derive from this would be energy of a photon will equal to hc over lambda. Right? So again, h is the Planck constant, c is the speed of light, right? So that means these two are the constant. So again, if you're looking at this, right, so E would still be inversely proportional to lambda. So that means if you have high energy of photon, right, you are going to end up with a smaller wavelength of that photon. Okay, so When can you use each of these? Does depend on what the problem asks you, right? So if the problem doesn't ask you anything about energy, then go with this, right? So if the problem asks you about energy, then it's depend on whether it's going to give you frequency or wavelength, right? You can use them according to what the problem given, right? What are the information given on the problem. Now let's take a look at how can we calculate the energy of a photon. Okay, so in this case, it's giving us this number with the unit hertz. Remember, hertz is the unit of frequency, right? So hertz is the same as per second. So therefore, in this case, you can actually replace this with per second. So because this is asking for energy and is involved with frequency, so I'm going to use E equal to h nu. This energy is going to represent energy of a photon. Okay, so then you need to just plug in the Planck value, right? So that's 6.626 times 10 to negative 34 joule times second, and then plug in the frequency as well. Note that the unit have to cancel out, so therefore you need to replace this hertz with per second, so that this second and per second can cancel out. So the energy of this photon will come in joule, right? But the problem asking in kilojoules, so therefore the last step would be converting from joule to kilojoule, right? So you are going to get this many kilojoule of a photon of light, okay, with this frequency. Next, we are going to take a look at the energy of 1 mole of light, okay, so emitted by a neon sign with a wavelength of 671 nanometer. Again, as I mentioned before, okay, so it's depend on what is given and what is asking, right? So it asking us energy, is giving us our wavelength, okay? So therefore, in this case, I won't be able to use E equal to h nu because h nu is related to frequency. So what I'm going to do is that I'm going to combine the h nu with the frequency, right, which is c over lambda. I'm going to combine this together. So I'm going to get E equal to h c over lambda because it's giving us wavelength, okay? So I'm going to plug in the information, right? So the Planck constant and the speed of light and also the given wavelength. If I do this, you probably notice that the unit of the wavelength and the unit of the speed of light, they are not the same. So therefore, you will not be able to cancel each other out. So you will need to convert from nanometer to meter first. Note that this value is the same as 6.71 times 10 to negative 7 meter. So if you do this, you probably notice that unit of meter will cancel out and second multiplied by per second, that can also cancel out as well. So your energy will come out in joule. Note that this joule is the joule of photon. Remember, all of these are of 1 photon. So therefore, in order to make them to be per 1 mole, you will need to incorporate Avogadro's number. Okay, so this is joule of 1 photon. So in order for me to convert this into joule per mole, so I need to multiply by Avogadro's number, which is 6.022 times 10 to 23 photon. You probably notice that I did not include 2 here. That's fine because the number of sig that is going to limit is going to be this 3 sig anyways. So the answer will come out to be 1.78 times 10 to the 5th joule per mole. Now let's take a look at the next example. A minimum energy of 498 kilojoule per mole is required to break the oxygen-oxygen bond in O2. What is the longest wavelength of radiation that possesses the necessary energy to break the bond of O2? So pretty much this problem asks us, right, so if you want to use radiation to break this bond right here, right, so what would be the wavelength of that, right? So that equivalent to the energy of 498 kilojoule per mole. Okay, so that's pretty much what it's asking us. So note that what's given here is giving us in energy. Okay, so this energy in kilojoule per mole. And it's asked us to find out the wavelength, which is the lambda. So that means if you think about energy and lambda, the equation that we are going to use would be E equal to hc over lambda, okay, because contain both energy and wavelength. Okay, so the problem with this is that this equation right here can only be used for just 1 photon. We cannot use this number yet because this number is of 1 mole. Remember, 1 mole is not equal to 1 photon, right? Because 1 mole is going to equal to 6.022 times 10 to 23 photons, right? So that means in this case, this amount of energy is going to be per this many photon. It's not per 1 photon yet. So we cannot use this equation yet. So therefore, the first step that we would need to take would be converting this kilojoule per mole to joule per photon first. before we can use the E equals to hc over lambda. Okay, so after that, then you can actually calculate for the wavelength lambda. Okay, so that means the first step we'll need to pretty much convert from kilojoule to, and because kilo means 1,000, so I'm just gonna multiply this number by 1,000, right? So that's how I convert from kilojoule to joule. The next step is to convert from mole to photon, right? So in this case, we will put 1 mole on top and we will put the number of photon on the bottom. Okay, so remember this is Avogadro's number is always going to be with an object, right? And this many object is equal to 1 mole. Okay, so we discussed this already in the previous chapter section. Okay, so there always be this many photon in 1 mole. Okay, so if you check the unit, the mole will cancel out. So right now you are going to end up with joule per photon. Okay, so the number that you receive here is going to be in joule per photon, which is exactly what we want, because in order to use this equation here, it needs to be in joule per photon. Okay, so if it's not in per photon, then you will need to actually convert it. So the next step is, since we already know the energy per photon, so therefore we can actually plug this number into here, right? So as the E, and then plug into the value of the constant Planck and also the speed of light to obtain the lambda. Okay, so E equal to hc over lambda. So because lambda, which is the unknown variable, is part of the denominator, so we need to do cross multiplication to get the lambda to be part of numerator. So I'm just gonna move that and manipulate the equation. So if I do that, I'm going to get lambda equal to hc over E. Okay, so I just did the simple algebra here. So now we get the unknown variable by itself. Okay, so the next step would be just plug in the known value, right? So the H and C value, and also the value of the E as well, which is the energy. You can leave the photon out in this case because this wavelength right here is already is going to imply that this wavelength is going to be of 1 photon. So now let's check the unit, right? So in this case, joule will cancel out. Second multiplied by per second, that's cancelled out. So your final unit will come out in meter. Okay, so if you plug into the calculation, if you get 2.40 times 10 to negative 7 meter, this is also acceptable answer as well. These two values are identical. Now, if the problem on the exam asks you to figure this out in the unit of nanometer, the next step that you need to take is going to convert from meter to nanometer, right? So another acceptable answer would be 240 nanometer, right? Because this 10 to negative 9 is equal to nano. So this problem doesn't specify what would be the unit of your final answer. So therefore, you can just leave it as meter, or if you want to, you can convert all the way to nanometer. That's fine with me too. It's turned out that this wavelength right here, right, is fall into the ultraviolet radiation. Okay, so all the UV radiation that can break the bond between oxygen and oxygen in the oxygen molecule. So shown here is the spectrum of infrared visible light and also the ultraviolet region that come from the sun, right? So you probably notice that the ultraviolet can be broken down into 3 regions as well. Okay, so the UVC, UVB, and UVA. And from our previous calculation here, 240 nanometer here, that is going to fall into UVC. Okay, so that is going to fall into UVC. So now from this spectrum right here, you probably notice that the ultraviolet region, right, has a shorter wavelength, and the infrared would be the one that has longer wavelength, right? Now, because wavelength is inversely proportional to the frequency, so therefore, in this case, the frequency of the ultraviolet would be higher than the frequency of the infrared, right? Now, in terms of energy, right? So energy is directly proportional to frequency, but inversely proportional to the wavelength. So therefore, in this case, the energy of ultraviolet would be higher than the wavelength of the infrared. Okay, so it makes sense. So that's why only the UVC region right here, right, that is able to break the bond of the oxygen molecule, not the infrared or not visible light. Okay, so now if you look at how the UV light get through our Earth, and because the high energy of UVC, right, can break the bond of oxygen molecule and other gases molecule as well, therefore UVC will be absorbed by all the gases in the upper atmosphere, right? So it will not be able to get to the Earth's surface, right? However, if you're looking at UVB and UVA, right? So these two are going to be able to reach to Earth's surface and will be able to interact to our skin. UVA has a higher wavelength than UVB. So therefore, in this case, you probably notice that UVA will be able to penetrate to our skin deeper than UVB, right? But because UVB has higher energy than UVA in this case, right? So it's going to cause more damage than UVA. Even though UV is necessary for the production of vitamin D in human, too much exposure to vitamin D can cause DNA damage that eventually might lead to skin cancer. And broad spectrum sunscreen can help protect us from both UVB and UVA. The last phenomenon that we are going to take a look at is going to be the atomic emission spectra, such as those that produce from hydrogen lamp or neon lamp. When you look at the white light through the diffraction grating or similar to prism, you will see that white light will produce all the visible wavelength. However, if you look at the hydrogen lamp, right, the light that produced from the hydrogen lamp is going to produce only a certain wavelength, as you see here, right? So these are going to be the wavelength that produced by the hydrogen lamp through the diffraction grating, or similar to prism again. So if you're looking at helium, right, so same thing here, helium only produce specific wavelength, right, of light. Okay, so as you see here. And if you're looking at other elements, right, so such as shown here, you probably notice that their atomic emission spectra also give off only specific wavelength as well. It doesn't give us the continuous wavelength as produced by the white light. So the observation that we can make for white light producing from the sun is that it's contain all colors, right? It's produce all the visible wavelength, right? And for the light that produced from hydrogen lamp is going to contain only specific color, which are violet, blue, and red. And from the helium lamp would be purple, violet, blue, yellow, red. Because white light produce all colors, so white light produce continuous wavelength, right? And the hydrogen lamp and helium lamp are going to produce the discontinuous wavelength. So therefore, the spectrum that you see from white light would be continuous spectrum. However, from those that produce from the elemental lamp, right, they are going to give us the light spectra because you see that it looks like light. The conclusions that we can draw from these observations would be white light spectrum is continuous. It consists of light of all wavelengths, right? And the emission spectra of the element, right, are not continuous. They consist of bright light at specific wavelength. And the light spectrum confirms the idea of quantum that the energy can be either absorbed or emitted by atoms only in a fixed amount called quantum. And the light emission spectra of elements can also help scientists to determine the composition of nebula in space as well, because each element will produce specific light spectra that are different from one another. So here is the summary of what we have learned so far. Okay, so we learned about the relationship between frequency and wavelength, energy and frequency, and energy with the lambda. So pretty much this energy right here is going to describe in of one photon. Right? So one photon of light, and photon represent a packet of energy of light, right? That light come as a fixed amount of energy. And this photon also going to describe light as a particle as well. We also learn about these phenomena as well, right, that lead to the idea of quantized energy or the discrete amount of energy of a photon, right? Please start working on paper homework chapter 3, number 7 to 10 soon, okay?